Well, good morning everybody. It's a Sunday morning today and I'm not really feeling like doing very much. I'm feeling quite lazy. It is a Sunday, late night last night. But I've been looking at this test sheet for the amplifier and I was going to say we've made disappointing progress on the test really. Or really, that's probably not very fair. I've made disappointing progress, haven't I? Spent far too much time waffling on and basically just getting lost in the woods. But yesterday we had a look at the frequency response, and after the cock up with the loudness control, we've corrected that now. So I think we can actually tick off this section here, which was the frequency response 20 Hz to 30 kilohertz. So I'm just going to put a tick in the box and we can move on, because I think we've done bandwidth to death, haven't we? So what I propose to have a look at today is I'm going to try and look at the output impedance of the amplifier, and linked with the output impedance is something called damping factor, which I'd never heard of before. So I think what we might just do is have a look at the damping factor. I've been doing some reading and looking at Wikipedia, and what damping factor is, it's a ratio between the output impedance of your amplifier and the impedance of your speakers. Okay, so without any more waffling on, which I have a habit of doing, let's turn my chair around and go to the bench. And before we do that, I'm going to show you this annoying bloody chair. So this is the chair. Gotta hate this chair. Everything squeaks. Oh, feel sick. Well, today I thought we'd start off by talking about damping factor, and as I said earlier, it's not something I've ever heard of before. So what is it? Why is it important? Why do we care? Well, this is our victim for today. It's just a speaker that I've found in the junk box, and we've got this connected up to the output of the amplifier. Yeah, that sounds really horrible. And I thought we'd start off just by torching a little bit. So we've got the signal generator connected to the amplifier, so we'll just switch it to the auxiliary line in input, and let's turn this signal generator on. Try 5 Hz. Right, I'm going to bring you in so you can see what's happening. And what we're seeing there is we're outputting a square wave from the amplifier into the speaker. So on the positive cycle of the square wave, let's draw our 0 volts through there very crudely. The cone of the speaker, the diaphragm, will be moving out. On the minus cycle of the square wave, the speaker diaphragm will be being pulled in. Now I've got the speaker now just connected to a DC power supply, and I can connect the power supply just by dabbing the connection to the back of the speaker. Now this isn't really something you should do, because what's going to happen is the voice coil of the speaker is going to heat up, and it's probably going to damage the speaker, and it's also going to damage the mounting, the suspension of the speaker. But to be honest, this is an awful speaker to start with, so we're not losing anything. So I'm just going to connect the DC power supply, and hopefully we'll see the diaphragm, the cone, will move forward. I'm going to take it off, and it moves back. So forward, off. Now that's like the positive half of the square wave coming from the amplifier. Now we're just going to look at the negative side. So I'm going to connect again. I've just reversed the DC connections on the back of the speaker. So this time when we connect, it's going to pull back. And I'm guessing just because of the mechanical construction of the speaker, it's able to actually move the diaphragm further forward than it is to pull it back. I'm guessing when it pulls it back, it physically comes up against a hard stop. It can't physically pull back into the housing any further, but it's able to go forward a lot more. Well, it's a few days later, and I've got to admit I haven't reviewed the previous part of the video, but I seem to remember I was messing around with loudspeakers and probably not really getting to the point about damping factor. With that in mind, I've decided to build a model and degrade myself still further by having a go at doing some woodwork. So believe it or not, this is my representation of a loudspeaker. So this metal ruler here, this represents the diaphragm of your loudspeaker, and that can move up and down, just like the diaphragm or the cone that we saw bouncing up and down on the loudspeaker earlier. I've kind of glued a magnet onto the end of this ruler, and I've actually got the coil bolted down. So that's opposite to a loudspeaker, where the actual voice coil is glued to the diaphragm, and that moves backwards and forwards. Well, I've reversed this. We've actually got the magnet effectively glued to the diaphragm, and that's going to move backwards and forwards. So what we'll do is let's just demonstrate this working if we can. So what we'll do is we'll just imagine that we're listening to some music and we get one of those really big high thumping drum beats. So what we'll do is we'll get a beat now, and you can see that the cone moved forward just as it did before. Okay, let's reverse the voltage, and that time the cone's just moved backwards. But there's something else happening here. We saw the cone moving forwards and backwards, but I haven't got any voltage connected at the moment to our speaker. But you can see the cone is still bouncing around. Well, although this is just a mock-up, something very similar happens in a loudspeaker. As you're playing your music, the cone of the speaker tries to move forward, and sometimes it moves back, but it doesn't always move forward and backwards to coincide with the music. The cone of the loudspeaker and the mass of the voice coil, it actually forms its own resonant circuit. So basically, if I just inject some noise into it, we get this oscillation. Now, the problem with this oscillation is that if that was a piece of music, you want to hear to your drum beat going dum, 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 dum. You don't want to hear to something going like that. So what damping factor is about, it's about the ability of your amplifier to actually control the oscillation of the speaker. Effectively, it's the ability of your amplifier to damp this oscillation. So I guess another analogy is that basically if you were driving along in your car, you might have springs on your car, but if you didn't have shock absorbers, every time you went on a bump, rather than riding over that bump nicely and slowly, as hopefully a good car does, every time you hit a bump in a road, you would bounce around in the car. And this reminds me a little bit of, do you remember at the start of the video when I jumped into my chair? And that was, I didn't actually do that on purpose thinking about this video, it just happened randomly. But if you go back and review that footage, when I jumped into the chair, I bounced up and down. Now, first of all, I'd like you to imagine that this is our loudspeaker, and we've actually got it connected to an amplifier that's got a very high output impedance. In fact, the amplifier's got such a high output impedance, we're not even going to bother connecting the speaker to the amplifier because it's ridiculously high. Anyway, so we're going to give it a twang, we're going to start the counter going, and I'm going to try and time how long it takes to stop. Okay, we're 15 seconds in, 20 seconds in, still quite a lot of bouncing going on. 40 seconds in, we're still bouncing, I can still see it, hopefully you can see that on the camera, but it's not bouncing quite so much now, it's just bobbing up and down a little tiny bit. And we're a minute in and we're still bouncing. Right, we're 1 minute 15 seconds and I think we've about stopped there. So the next test that I'm going to do is we're going to imagine that we've got an amplifier that's got a low output impedance. Got the loudspeaker plugged into our amplifier. Let's just see if the amplifier brings this oscillating speaker under control any quicker. So what I'm going to do is put the finger on there again. 1, 2, 3, 4, go. And I think that stopped, and we're about 25 seconds in. Let's just make sure that wasn't a fluke. 1, 2, 3, 4. And I think that stopped again. So what we'll do is we'll just disconnect our amplifier. Better switch it off actually so I don't short anything out. So we've got our speaker leads disconnected now. So we're going to go back to an example of a high impedance amplifier. We've got no connection to our speaker. Need to zero that. And right, hold that down. Let's do it on 3. 1, 2, 3. Go. There we go. Well, we're over 20 seconds now and it's still bouncing around quite readily. 40 seconds in, still bouncing. 45, still bouncing. 50 seconds, still bouncing. 60 seconds, still bouncing a bit. Right, it's getting hard to tell now whether it is still bouncing, so I think we'll stop it there. Yeah, it is still bouncing though, I can still see it. So I might have even stopped it a bit earlier there. But what was that? Was that 3, 4 times? That was basically oscillating for about 4 times longer. So what was I trying to say with all this messing about and waffling? I'm trying to say that the output impedance of your amplifier directly affects its ability to control the resonance of the loudspeaker, and that the resonance is very undesirable. Now, in order for us to work out the damping factor of the amplifier, the first thing we need to do is work out the output impedance. And that means we get to play with some test equipment. Wahey! So what we've got set up here is, here's the amplifier that we're going to be testing, which is the Kenwood KR2600. Now we're going to be driving the amplifier with a signal, and that signal is just going to come from the signal generator. Most people conduct this test, I believe, at around 40 Hz, so that's what we're going to be doing. And the signal generator is connected using the 50 ohm output of the signal generator, and that's connected to the left line input of the amplifier. And we're going to measure the output voltage using the BK Precision 5491A multimeter. Now, as you can see here, the multimeter is directly connected to the output terminals of the amplifier, and it's going to remain connected for the duration of our test. We've also got a dummy load connected to the output terminals of the amplifier, but we've got it connected via this link here. So what that allows us to do is either connect the 8 ohm load or disconnect it very easily. So in order to do this test, we need to know 3 things, which is the load resistance, which we can measure. We need to know the output voltage of the amplifier when there is no load, so that will be with this link disconnected. And we also need to know the load voltage when the load is connected, so that's with this link in place here. So when we know all those 3 things, we can plug those numbers into this simple formula, and that's going to give us R out, which is the amplifier's output impedance. Once we know the amplifier's output impedance, we can work out the damping factor using this formula below, and that's really quite a simple one. So all we actually need to know to work out the damping factor is the speaker impedance, which is whatever impedance of speaker we choose to connect to the amplifier. In our case, we're going to use an 8 ohm speaker, and we're also going to use our amplifier output impedance, which we've just measured. So if we divide one by the other, that's going to give us a damping factor. So all that's really quite straightforward. Now, the voltage levels that we're going to be doing the test at, we're going to be doing it at approximately 2.8 volts, which is 1 watt, a 1 watt load into the amplifier. Now it's quite important to do this test at a fairly low output voltage, because if you're not careful, what will happen is the output voltage of the amplifier will sag because it's pulling too much current into the load. And if that sags, if that sag occurs, the voltage drops, and that's going to produce a misleading output voltage, and it'll make the test invalid. So, you actually only want to do the test at quite low power. And as I say, I've chosen 1 watt, and this amplifier is a 15 watt rated amplifier. Okay, that's enough waffle. Let's have a look at what this looks like on the bench. Now, in order to do this calculation, we need to know the resistance of the dummy load, and also anything that will add to that resistance, which would include the resistance of the cables. So this is a cable that I've got here, which is going to be connected into the dummy load. Anyway, what we'll do is we'll plug these leads into the back of the dummy load, and what that will do is that will take a resistance reading, and that will be the dummy load plus our connecting cables. Again, I'm just wobbling these around in the back a little bit to make sure they've got a good connection. So we'll just do the test now, and I'm hoping it's focusing on that. At the moment I've got the dummy load set on its 8 ohm range, and it's giving us a reading of 8.4 ohms. Now, because I've got a memory like a sieve, I've forgotten what that initial resistance of the meter was, because I just want to null that out just to get it even more accurate. Right, that's 0.02. I was going to bother to take that 0.02 figure away from these, which is just this resistance of these cables, but to be honest, I don't think it's a big deal. We won't bother. So importantly now, we know what the resistance of our dummy load is, and we know what the resistance of the connecting cable is that we're going to use between the dummy load and the output terminals of the amplifier. So we've got the voltmeter now connected right to the output terminals of the amplifier using these fairly thick cables, and we've got the dummy load also connected to the same output using, again, the thick cables that we saw earlier. So at the moment we've got our signal generator set up, and that's outputting to the amplifier a 40 Hz sine wave, and the outputs from the amplifier are open circuited, i.e. we aren't connected to the dummy load at the moment. I've pulled out one of the connectors. So the voltmeter here is measuring the open circuit output voltage from the amplifier, and that's showing 2.82 volts at the moment, which would effectively be a 1 watt output if we were connected to an 8 ohm load. So that's going to be our open circuit voltage, so we need to make a note of that for our calculation. So 2.821 at the moment, 2.821. So the next step is to plug in the dummy load and then record the voltage under load. And we've got 2.740 volts. 2.740 volts. So what we need to do next is we just plug those numbers into our calculator, and that's going to tell us, hopefully, what the output impedance of this amplifier is. So we'll take our no load voltage, which is 2.821, minus our loaded voltage, 2.740, equals, and we'll divide that now by the loaded voltage again, 2.740 equals that, and we multiply that result by the load resistance, which was 8.4 ohms. Multiplied by 8.4 ohms equals 0.24 ohms. So our output impedance, this amplifier, is 0.24 ohms. And to be honest, I was actually expecting about 0.3 ohms in my head. I don't know why, that's just what a figure I've had. I've heard 0.3 ohms quoted for various amplifiers. That's been solid state amplifiers, transistor amplifiers. I've heard that quoted as kind of a standardist figure in the past. So quite happy with that. So from that we should very easily be able to work out our damping factor. So the damping factor, which I've got written down here, it's simply the speaker impedance divided by the output impedance of the amplifier. So our speaker impedance, let's say it's nominally 8 ohms, and our amplifier output impedance was 0.24. 0.24. So let's just do that. 8 divided by 0.24 equals 33.3. Now the specification for this amplifier said the damping factor was 30 and we've measured it at 33. So hey, I'm having that. Yay. Back of the net. What a Bobby Dazzler.